Here's one question that I found from RIT website, good example, and one of the students had this on their exam and brought my attention to this problem because they needed help. So I decided I'm gonna record this video that might help more people than just my students. So find the area of the region enclosed by the following curves. One curve is x equals to y squared minus 2, and the other one is x equals to y. So every time you start this type of problems, you want to graph the graph first. So let's look what the graph is going to look like if you graph x equals to y squared minus 2 and x equals to y. So here is the graph, and I need to know the points where the graphs intercept. So these will be my integrations, or I can also calculate this one. So this one is -2 and 0. The other 2 points, I'm gonna set y equals to x equals to, another one is x equals to y squared minus 2. So because x is equal to y minus 2 at this point on the top and on the bottom in yellow, I can set y is equal to y squared minus 2 and find my points where those two graphs intercept. We'll have quadratic equation, and then we will have y minus 2 and y plus 1 equals to 0 if we factor out our trinomial, and we get two solutions. Y is equal to 2, this is where 1 time the graph intercepts, and y is equal to -1, this is where the second time the graph intercepts. So my points are going to be -1 for y here, and my point here is going to be 2. Because x is equal to y, then x is also 2, and because x equals to y line is in the bottom point as well, so we can say this one is -1 as well. Because it is easier to integrate with dy function, so we will have x equals to y squared minus 2 and x equals to 1 instead of solving it for y. Our points of, or the limits of integration are going to be on y as well, because it's going to be dy. And the lowest point on y is -1, and the highest point on y is 2. So I'm going to have the integral from -1 to 2, and then I have to look at my graph differently now. I'm going to look with respect of x being my y axis and y being my x-axis. And if I look at the graph, so if I turn it around, let me just redraw it this way. If this was my x and this was my y, the graph would look like this with a line like this, and we would be looking at this part. So you would have a -1 on this side and a positive 2 on this side on y. So these are your points of integration, and then the top function is x equals to y, and the bottom function is x equals to y squared minus 2. Because my top function is y equals to x, then I'm going to have y as my top function, dy, minus, and then I have the integral of -1 to 2, and then the second function is y squared minus 2. If I take the integral of the first function, we will have 1/2 y squared, and then for the second function we will have minus, and that one is going to be 1/3 y to the third minus 2y, and I forgot dy over here. If we distribute the negative over the parentheses, we have 1/2 y squared minus 1/3 y to the third plus 2y, and then we have to keep our points of our limits of integration, so it would be from -1 to 2, and it would be from -1 to 2. Now if we plug in our numbers, we have 4, 2, for the first one, I have 2. If I plug in 2, minus, if I plug in 2 over here, I have 8 over 3, and then plus 4. And then for the second one, I'm going to plug in negative 1. So minus, and then I'm going to plug in negative 1. I have 1/2, and then I have positive 1/3, and then I have negative 2. Now, taking away the parentheses will give me 4, negative 9 over 3, and plus 3.5. And calculating these ones, my final answer is going to be 4.5. This was a good example where the functions, or the first function, y squared minus 2, or x equals to y squared minus 2, was better defined as a function of y, and instead of taking the integral with dx, respect to dx or x, we took the integral with respect to y, or using dy.